Okay, in this lecture we're going to look at libraries and clients, and so this is about how do we build increasingly levels of complex software by reusing existing pieces of software. And then we're also going to have a little look at a particularly useful part of Java, and it's available in many programming languages, a method called printf, and this allows us to format text in a very nice and pretty way, and it's something you'll be using in some of your programming assignments. But before we start, let's have a little look at where we've been and where we're going. And so, as you recall, in the beginning of the course, we looked at things like what are variables, how do you declare them, how do you change their values, assign them values, compare them against one another, and so on. We looked at input and output of text using we're using a helper class called standardin. So standardin can read input from the user interactively, or it can also read input from a text file. We've seen calling some methods in the math class, so things like math.random. So getting rather than having to implement our own random number generator or our own function to compute square root, we've reused some code that was provided by the folks who developed Java. An important part of any kind of programming language is conditionals and loops. Conditionals allow us to skip a certain section of code, so things like the if statement, the if else, the switch statement, these are all examples of conditionals. Loops, often we want to repeat the same section of code many times, so rather than cut and paste it 100 times, we write something like a for loop or a while loop or a do while loop to repeat that section of code. A common thing you might want to do in a programming language is have a big set of related data, so have a big table holding all the scores for all the students in a course or some such, and arrays provide us that capability. Just text input, text output, a little bit boring, so we've seen how to do graphics, and again we're using a helper class called standard draw. It makes it easy for us to draw things, draw circles and colored lines and things like that. We're also using a helper class called standard audio that allows us to play audio files and even create our own sampled audio. Where we are now is we're going to look a little more at functions and modules. So how do you build more and more complex software by combining existing pieces of code in interesting and new ways? And then where we're moving to in future lectures is we're going to look at objects. So how do you build your own data types? So rather than just use the primitive types provided by Java, how do you build your own data types that sort of encapsulate and represent the structures you're using in whatever problem you're trying to solve? Here is our dice rolling example, which we've seen before. And while you could write any program you wanted to by just putting all your code in the main, it's a solution that just doesn't scale. You're going to have lots of bugs in your program. No one's going to understand it. You're going to end up repeating a lot of code. So here I've had to type the same thing repeatedly, and that often is not only tedious but often leads to bugs. So there's our little friendly neighborhood mosquito reminding us that repeating code like this is generally a bad idea. And as we saw in a past lecture, one way to address this is to take that functionality and wrap it in a class. So I made a static method called getRandomNumber, and that encapsulates the functionality that I want to draw a random number between some start point and end point, inclusive of the endpoints, and does the calculations. And then I can simplify my program, and I still have this bug. I keep trying to get rid of this bug from my slides, right? If you roll 2 dice, you can never get 1, and this code actually has a bug. This do while loop can go into an infinite loop. If target happens to be 1, which will happen 1 in 12 times, this program never terminates. So my bad, I keep forgetting to change the slides. You can see how easy it is to make mistakes, but even with this helper method, I still made a mistake in my arguments to the helper method. So this really should be 2, 12 here. But I have eliminated the potential for screwing up other parts of it, like how do you do this calculation of drawing a random number between the start and the end point. You could have done it the way I just showed you. So I made this a static method inside the dice rolling class, but maybe other people in the world besides my dice rolling program want to use this static method. So I could take that method and maybe some other methods that do different forms of drawing random numbers and package them up into my own class called random util. And I'm going to show you later in the lecture. Princeton has a standard random class, which has a lot more than sort of my little simple random util class does. But it's the same idea. They've packaged up all these methods that do things related to random numbers and put them into a single class. And then other people that want to use it can go ahead and use it. This is also an example of a overloaded method. And recall, overloaded methods are methods that have the same name but different numbers or types of parameters. If I call getRandomNumber with 2 integers, it's going to run this first version, which draws between the start and the end point inclusive of the endpoints. If I call it with just a single integer, it's going to assume that start part of the interval is 0. And that's just, it's not that you need this second method, it's just maybe there for convenience, so people don't have to type 0 comma all the time if that's something commonly they want to do. And that's my choice. I was the designer of this particular class, and so I decided I wanted that convenience method. And different people doing that development might make different decisions about whether to include a method like that or not. At least for this course, we're going to simply place these classes that have all these sort of utility methods. We'll just put them in the same directory as the program that's using them. So whenever you use standard draw or standard audio or standard in, you just put that class, the .java file, in the same directory with the Java program you're developing, and then Java will find it just fine. There are other mechanisms for doing this in Java, and you can learn about those online, but as far as this course goes, it's just simpler. We'll just copy the files into every directory we need to. All right. Whenever you try and refer to a method in this library random util, you need to preface the method name with the name of that class. So these things are all living in a class named random util, and that's in a randomutil.java file. And whenever I call getRandomNum, I have to use this so Java knows that it's not a getRandomNum method in myself, in the class that I'm running. It's not anywhere in dice rolling. It's in a different .java file that it's going to look for in the same directory. And that's an important distinction. So whenever you call these static methods, you always preface them with the name of the class. And by convention, we're always going to name our classes starting with uppercase. And you can tell I'm calling a static method because what I have here is something that begins in uppercase. We always name classes starting in uppercase and then uppercasing every new word, whereas methods and variables we start in lowercase. And the main reason we do that is just so it's easy to tell the difference. I can tell I'm calling a static method just by looking at the difference in case. Just because this starts with a capital R, I know that that is a call to a static method in that class. Here's some terminology. So this random util is a library, and it's just a normal Java class, but it exists mostly just for other people to call. It's just a collection of useful things, just like standard draw is a collection of useful drawing methods. It's a library that just exists for other client programs to call. And when I talk about a client, I mean the program that, it's normally the client is what you're developing. It's the program that solves your particular problem, and it makes calls to the library doing just what I showed you on the previous slide by calling the class name. And in this case, this example code is calling a library called Gaussian, and Gaussian implements a variety of different methods associated with the normal distribution. So this is that, that bell-shaped curve that often occurs in science and nature and so on. And they have different methods in there. And when we talk about the API, that's the application programming interface, and it's the set of methods and sort of what do they take for input and what do they promise to give for output. And in this case, we've got two different methods, and so they've kind of the Princeton class here has kind of violated this notion of method names always starting in lowercase that I was just on about a few slides ago. But that's because there's a in math there's a they're talking about a lowercase and uppercase phi variable in the mathematics. So they decided to violate the rule in that case. The implementation is actually the code. If you go into Gaussian.java, you'll actually see the Java code that implements each of these static methods. The important thing though is, as a user of this library, if you just want to use this Gaussian and you just want to know what's the probability of a certain value given a curve with a certain mean and a certain variance, you can just make calls to this library and call its methods, and you don't really actually have to understand the implementation. And that's the beauty of libraries and modular programming. You can let somebody else do certain bits of the implementation, and you can just trust that they did it correctly and just make calls to the methods that are supplied by the library. Let's talk a little bit about random numbers. Here's a quote from a famous computer scientist talking about random numbers. And we've been calling math.random, but computers are actually deterministic. They can't really produce randomness themselves. They're pseudo-random. They use a mathematical procedure to simulate randomness, and for most purposes, and certainly for things we'll do in this course, that's random enough. And but they can't, in fact, actually really be random unless they do something a lot more sophisticated. And you might be interested, you could go check out this website, random.org, and they actually produce true random numbers. And the reason they can produce true random numbers is they don't just have a computer running a bit of software. They actually are sampling atmospheric radiation or some such in order to generate randomness from nature. And you can go there and you can ask it to flip you coins and stuff like that, and we'll actually use this sampled radiation to determine what results you're going to get from your coin flips. So true random bits are actually valuable, and you can actually buy. People sell CDs containing an entire CD of random data, and that's actually valuable. And for some applications, it's important that you really have random numbers and not these pseudo random numbers that are generated by your deterministic computer. As I said before, the Princeton guys have a much more complete random library than my little random util that only has two methods. And this library, here's the API, and this is kind of the standard format. When I show an API in an assignment or in a lecture, this is usually how we'll present it. Here's the name of the library, so it's living in a file called standardrandom.java. And here are the lists of methods, and I'm providing you with the return type, the name of the method, and then the parameters to the method. So given this input, it's going to produce some output. And what does it exactly do? And usually an API will give a short description that describes what that particular library method does. And the cool thing is, by just looking at this API description is all you really need to know. You don't actually have to open up standard random. I mean, you could go into standard random, and so here's Eclipse and here's my standard random. And if I wanted to know exactly what standard random is up to, here's the actual implementation of various methods in standard random. All right, but maybe I don't really care exactly how they're generating a real number from a standard normal. All right, I just want a number from that standard Gaussian distribution. So I can just call this method and get one, and I don't have to really exactly worry about the specifics of the the Box-Muller transform that they're using to generate this number. Yeah, and so here are just some examples of various methods and the actual implementation I just showed you in Eclipse. You might be interested to learn that actually standard random has a main method. Normally when you develop a client program, your main program, that's kind of like the that's the business end of your program. It runs and solves the problem you're actually interested in. But if you go into, so we can go back into Eclipse and look in, if we go to the bottom of standard random here, you'll see they actually have a main method. And every class you have in Java can have a main method. There's no problem having multiple main methods. What happens is whatever program you run is the main method that gets executed. So from the command line, if I were to type Java standard random, it would actually run this main method. Now for things that exist just to be a library like standard random, often what you will do in this main method is just exercise the methods. So it's doing a unit test and calling its various methods and just printing their output. So it's whoever developed the library often will produce a test main as part of their development of the library. Here are a couple runs. I'll just show you them in the slides. If I went to the command line and typed Java standard random and 5, it's going to draw a random number seed. And so recall that I said random numbers generated by your computer are deterministic. But they're pseudo-random, and they do this by basically having a seed, and they get this seed from something like the looking at the milliseconds of the clock or the date or something like that. It's pretty unpredictable for most purposes, and if you're just making a game or something like that, it's random enough. And this particular run here was the random number seed, and what this seed influences the sequence of random numbers that are going to be generated. And so then it loops around and generates 5 things, generates something from a uniform distribution, something that's a coin flip, and then it's drawing something from a Gaussian, a normal curve, I think the mean centered at 9 and with a variance of 0.2, so it tends to hang out near 9.0. That's one particular run of the unit test of standard random. Here's a second run, and notice we've got a different seed value because the clock has changed, and so however it's drawing the seed number, it's getting a different random number seed, and because it has a different random number seed, it actually gets a different sequence. These random numbers are different from the first run. This unit test, though, notice you can actually specify. If I give it a second command line argument, it's going to actually use that command line argument as the seed. So rather than using the clock or whatever it does, it actually takes that command line argument and uses it as the seed. So if I take this seed from my first run, put it into standard random and run it again, I actually get the identical set of random numbers. So they're not truly random, they're just pseudo-random, and if you condition on the same seed, you're going to get the same random numbers. And you may or may not want this. So this is kind of nice if you've got a program and you want to have a reproducible, it's using randomness, but you want to reproduce a run. One thing you could do is seed the random number generator, and then your program is going to do exactly the same thing it did during the first run. Whereas if you don't seed it, it's going to produce a different random sequence. Using a library is quite easy, and here's a very basic example. Random points. It uses a standard random, and it draws something from a Gaussian centered at 0.5 with a variance of 0.2. Alright, that's the x-coordinate, and then a y-coordinate is similar. So this is drawing points from a two-dimensional normal distribution, and then it draws that. Alright, and we can run it here, it takes the number of points from the first command line argument, so we can ask it for, I don't know, should I ask it for 1,000 points? Alright. Oops. Didn't exactly run the right program there, did we? Doesn't seem to be convinced it wants to run. There we go. Now it's running. I got to move my. So here it is drawing the 1,000 points from the two-dimensional Gaussian. You can see the points are more distributed near the center, near 0.5, 0.5, and then you get some outliers around as you get further and further away from the center. And without having any, without having to do any work about how to get these points from the Gaussian distribution, I'm able to generate this program quite easily. And that's the beauty of libraries and modular programming, is I can leverage the work of past programmers to get my particular job done. And again, you always preface. So here I'm actually using two libraries. I'm using standard random and I'm using standard draw. And as usual, we have to put the name of the library before the call to the static method. I'm going to show you a little more sophisticated example of modular programming. And here is what we're trying to do. We're trying to flip coins. We're going to flip a certain number of coins. Say let's flip 20 coins and count how many times did we get heads. And then we're going to repeat that experiment and see, how often did we get 20 heads, how many times did we get 19 or 18, 17, and so on, how many times did we get 21, and so on. And then we're going to compare that to the theoretical prediction. So this should come out to be normally distributed. So it should follow a Gaussian distribution with a mean centered at the number of coin flips. And let's go ahead, and I got this program in here. We can run it. Okay, I'm going to convince this thing. Always likes to run the wrong program here. Let's run Bernoulli. Let's just run it for, say, we'll flip 20 coins and we'll do it, I don't know, 20 times. Okay. I had to move my window, always pops up on the wrong screen. And you can see, well, yeah, here's the theoretical prediction, which is this line, and we flipped 20 coins and we got some, but we didn't even get any in the middle here. It's kind of noisy. I can put that one over here. We can run, let's crank up the number. Let's run with 200 points. So 200 separate. So here's 20 and here's 200. Okay, looking perhaps a little more reasonable. Let's run it with 2,000. Alright. And you can see it's starting to match the theoretical predictions a little better. It's still a little lopsided, and this is, every time I run this, I might get another one. So if I run the same thing with 2,000, okay, and I show you both of these. So here's the one I just ran. Here's the one I ran previously. Okay. The randomness in it, I'm not seeding the random number generator, so I'm getting different coin flips every time. Each time I get a slightly different look to my curve. But if I crank this up even further, so instead of doing 2,000, let's do 200,000. So I'll go up by a factor of 100. All right, now it's looking, much closer to the theoretical predictions. We could crank it up again. Another 2 orders of magnitude, and still seem, well, there it is. It's running. It's working hard. I'm not sure how. Oh, there we go. And it's now a closer match, though it's kind of, it doesn't look that much different than the one I ran before. Let's have a look at the program that does this. So you might think this is involved a whole lot of code to do that. But what I'm doing is I'm leveraging all the work of the people that made the libraries I'm using. And I've split my program up into a number of different parts. my Bernoulli program has to run this coin flip trial. So given a number n, like I was running with 20, flip 20 coins and sum up how many heads. And this is something I created. So I created a little static function called binomial. It has a variable heads, and it just sums. It just flips fair coins and sums up how often we get heads, and then it returns that value. So that's one instance of my experiment. All right, here's the main program that's running Bernoulli. First I get that n value, then I get the t value, the number of experiments from standard or from the command line. I'm going to create an array that tracks how frequent I got a certain number of heads. So maybe, sometimes I got 20 heads, sometimes I got 0 heads. And I'm going to use this array to put that value into this frequency array. I'm going to run a whole bunch of trials. So I'm running my t trials, and then I'm seeing how frequent did I get. Given I flipped 20 coins, how often did I get 10? How often did I get 20? And actually, I misspoke when I talked about this, right? This center here is presumably not 20. 20 is very unlikely, right? This is actually 10. Okay, sorry about that. So if you're flipping 20 coins, you're very unlikely to get 20 heads, right? You're more likely, on average, you're going to get about 10. So sorry about that. I misspoke. I just realized. And that's why they create an array here that goes from 0 up to 20, because you could, you flip 20, you could get all tails, or you could get 20 heads. And so there are basically 21 different possibilities of the number of heads or tails you could get. This loops around and just calls this thing to generate each particular trial. All right. So thus far we haven't really used any libraries, but now I'm going to actually use a library. This is the standard stats, and it has something that plots that bar graph. And what I first do is I create a normalized version of that frequency data. All right, I take that frequency count and I divide by sort of the maximum number I could possibly get. All right, so assuming all the trials happen to land in the same thing. So I create a normalized version, and then this just plots those that bar graph you saw in the example. This is what's plotting the theoretical prediction. So that's plotting the actual Gaussian curve that would be theoretically predicted given this problem. And so it takes the n divided by 2. So this is the 20 divided by 2. So that's why you get, the mean is 10, not 20. And then here's the standard deviation, the square root of that number of flips divided by 2.0. And then it plots the Gaussian curve. It creates basically a double array of the sample points, and then it just calls standard stats.plot lines, and that plots it. And that's the program I just showed you. This program is actually making use, and so let's just focus on the Bernoulli part of this graph. This is an example that I think is also in your textbook. My program Bernoulli made use of a bunch of different libraries, and the first library it uses is actually just to get the command line input. So I'm calling a library integer dot, and so that has a bunch of utility methods for doing stuff like parsing a string into an integer. I use that library. We saw the 2 calls to standard stats, all right, plot bars and plot lines. Up here in the binomial method, I'm calling standard random to flip my coins, so flipping things according to the Bernoulli distribution. Standard random in turn, so I'm making call, I wrote Bernoulli. Bernoulli is calling standard random, and standard random in fact is calling math.random. It's using the math library. Okay, and I'm also making calls to Gaussian, and Gaussian is also making use of the math. What we have here is a dependency graph, so each edge in the graph shows who depends on what. So in order for me to run my Bernoulli program, I need to have access to the integer library and the standard random library and the Gaussian library and the math library, and it turns out standard stats, it's actually doing drawing, so it needs a standard draw. So actually I need all of these guys over here, okay, everybody but standard array IO and standard in. I need all these other classes in my directory in order for me to run the Bernoulli program. And actually, if you see in my Eclipse project, I've got all of those different ones. So I've got some that I don't need in here as well. But if I failed to have something like standard draw in this project, it would fail to run this program Bernoulli because there's a dependency. And so it's important to understand that you need to make sure you have, if you're going to use a library, make sure you have that library and anything that library depends on. And you can see often, at least a lot of the Princeton examples, they actually list the dependencies, and so if I'm running Bernoulli, I also have a dependency on standard draw. All right, so let's switch gears and let's talk about printing text. I'm going to show you a particularly handy and very common way to format text output using something called printf, and it's a tried and true method that's in many programming languages. Java has it, other languages like C++ or Perl or PHP, these languages all have it, and it's got a little funky notation you have to learn, but once you learn this notation, it's knowledge that's transferable to a lot of different programming languages, and it really is a nice way to encapsulate program output. And in Java, we're going to be using, just like there's a system.out.println, there's a system.out.printf. And to get this pretty text formatting, you want to call the printf thing. And whenever you call printf, you're going to get some output to your standard output to your console window. Whereas if you want to take your input and put it into a string variable, you want to call something like string.format. And so I'll show you the difference. But basically what I'm going to show you about how to do the pretty text formatting is the same regardless of whether you're calling printf or whether you're calling string.format. Here's an example. So I've got a double variable and I've got a float variable. So these are both floating point values. It's just that doubles are a little more precise than floating points. So by default, if you just have a decimal, it's going to be of type double. If I want a floating point, I actually have to stick this little f on the end of it. And here are two calls to the printf method. It's going to print out d is about, and then look what it prints. Here's the actual output, d is about, and notice how many decimal places I have. I have all the way out to 9, but when I use the printf, it actually rounded it to 6 decimal places, or actually looks like it just truncated it to 6 decimal places. Is that actually true? Let's run it. I've got the same program in Eclipse. Oh yeah, it did round it, so sorry. My mistake. This is actually rounded, so it's not 5, 6, right? It's 5, 7. So it's rounded the 6 to a 7. All right. And what's happened here is it's taken this, so let me go back a slide here. It's taken whatever is in this variable d and filled it into this %f slot, and it's rounded it to 6 decimal places, which is just the default of what Java does. If you don't tell it how many decimal places it wants, it rounds it to 6 decimal places. I also wanted to go down a line, and so printf does not go down a line. So if you call something like println, it goes down a line. But to make printf go down a line, you've got to put in this \n, which is a secret code for a line feed. You don't always have to have 6 decimal places. You could have a different number. And here's an example of getting 1, 2, 3, or 4. All right, and I'm printing out different values of pi. So math.pi, obviously in the math library, there's a constant called pi, and it has, it's got a giant number of decimals after it, but I can also round it to get different approximations of pi. You can also do something similar with scientific notation. So if you want to express the speed of light as in scientific notation, you can use the %e. So here I use %f, here I use %f, but I added a little dot and a number, and here I've switched to %e. And whenever I use %e, Java is going to format it with this notation of 2.99792 times 10 to the power of 8. You can do a similar kind of text formatting using integers, but whenever you use integers, you have to use %d. So instead of %f, we've used this %d code. And what happens is you can actually put multiple percent codes. These are it's kind of like a template. This first string, whenever you have printf, you have a string, and in that string you specify the template, and it's going to fill into these percent codes stuff that appears after that string. And I've specified a %d here and a %d here, and so I must specify two variables afterwards. So I have a comma separated list of variables, and it fills in power for this %d, and it fills in I for this %d. And this thing's going to loop from 1 to 8, computing powers of 2. Let's say you want it to print a little prettier, like say I want the equal signs to line up. I could do this. I could put a 5 instead of the D, and what the 5 says is please make this thing a minimum of 5 characters in width. And by doing that, it aligns this, and I get a very nice nice printed output. So let me open, I've got an integer version, so this is the same thing in Java, so you can see you get the same output. And I could crank this up, so I could, for example, go up to the power 2 to the 16. Alright, and I get very nice aligned data. I could go up even higher, 2 to the 32. Alright, that thing I put before the D specifies the minimum, but not a maximum. So if I get a really big number that's bigger than 5 characters, it's just gonna, it's not gonna truncate it. It's just gonna no longer align as nicely. So I could increase, and I could say, oh, please put, give me 10 characters, and if I run this, alright, now I've got my nicely aligned equal signs again. You can also specify other flags. For example, if by default, when I use this %5, I'm saying give me 5 characters of minimum width for this particular field. If I put a minus in front of it, it's going to left justify instead of right justify. And here's the difference in the output. And I could do the same thing in my program here. If I put a percent there, or a minus sign there rather, and then run the program, now those numbers are left justified. There are other things you can do. You could use a comma. This will specify please put commas between groups of 3 digits, and there's the output for that. You can also use percent codes to put in text. %s refers to a slot for use with a string variable, whereas %c refers to a slot that's for use with a char, so a single character variable. And here's the output. It's putting the string variable name into %s, and then the other string variable into the %c code. And you could do this same thing just using what you already know with system.out.println by just using string concatenation. So here's exactly the same, produces exactly the same output, but without using the printf. The advantage of this is it's maybe, if you get enough of this going on, of you've got a string and then you concatenate and another string, and this can get kind of hard to read, whereas I think sometimes it's easier to use a printf and put in some %s slots and then put all your variables afterwards. Alright, but there's more than one way to skin a cat. All the prior examples all use printf, and they always output. Whenever you do a printf, it's going to output to your console. It's going to output to standard output. If you actually want that formatted thing to live inside a string variable, you can use string.format. So it's just like system.out.printf. It's exactly the same format specifiers and the same percent codes. You still need to fill in give a list of the things to put into the slots you're providing. But it doesn't print a console, it actually returns a string. And so I can open this one up. All right, and we can run this. Shall we run this one in the debugger? All right, here's the beginning bit. All right, that's just showing you that those two things print equivalent things, but here's the part I wanted to look at. I've got a string variable called lines. It's initialized to the blank string. All right, so recall that the default value of string is null, and so if I actually want it to start out as a blank string, I have to actually assign it equal to double quote, double quote. I go into my for loop, and after the first for loop, you're going to see the lines variable is now changed. All right, it's random num 0 equals 0.62, and you can actually see, at least in Eclipse, it's showing you that /\n. I haven't printed anything. Notice there's no output in the console window. All I've done is concatenate to that local variable called lines. If I loop again, I'm now going to add a second line, and it's just glommed on, after the /n, and it repeats 4 times. All right, still there's no output. All I've done is put all that output inside of my lines variable here, and then if I were to then print that lines variable, it would display all the output at once. String.format's convenient if you need to do some sort of printf style formatting, but you want to delay, or you don't actually want to print it to the screen. You want to do something else with the output. I haven't talked about all the things you can do. Here is the sort of list of describing the things that can be done with this format specifier. So this is that percent code, and the things that are required when you have a format specifier are the percent and the type. All these other bits are optional. And what do they do? Well, this last one, the type is required, and this is like the D or the F or the S or the C. That specifies what kind of data type you're putting into this slot. You must always have that one. If you've got a floating point and you want to specify the number of decimal places, you can do dot and then how many decimal places you'd like, so something like .3. We saw you could use a width, so before that, dot, or maybe if you're just using, an integer or something like that, you can just have the width. This is just a number specifying the minimum number of characters that this slot is going to consume. You can put things in the flags, so this would be like inserting commas or left justifying instead of right justifying by using the minus. And then finally, argument number. This isn't used that often, but if you want to repeat things in your list in multiple slots, you'd use this, but I don't need to really worry about that. And here's an example down here. Printf percent comma 6.1f, and then I'm putting 42. So here are the different parts. So we basically got everything but that argument number. We have the percent, that's required. We have the f, that's required. But I'm also specifying, please output it with 1 decimal of precision. Use a minimum of 6 characters for this slot, and then please put commas between groups of 3 digits. With great power comes great responsibility, and things can go wrong with printf. You must be careful that you specify the right percent code, so that type that's F or D or S or C or something like that has to match the data type of the variable you're trying to put in the slot. You also need to be careful to match the correct number of arguments. So if I've got 2% D codes, I better have 2 integers in this list, and I don't. All right, and so this will compile, and so I can show you this program. Where's printf? Printf gone wild. Eclipse is not going to protect you, or the Java C compiler isn't going to flag this as a compile error. it's happy as a clam that you're trying to do this. All right. When you try and run this, however, it's not going to be happy as a clam. You're going to get a runtime exception. In this first case, we're trying to put a integer into a %f. And you might think, well, why doesn't that integer promote to being a floating point? And well, it doesn't. Okay, it's printf's even more picky than Java is with your typing. It doesn't want to put this integer into a % code. If I wanted this to work, I would have to do something like cast that, and now that line will be happy. Okay, but now it's going to crash on line 13 because I'm trying to put a floating point value into %d code. That also is a bad idea. So if I wanted that to work, I would need to do a cast. And now I fix that and I run it and I get another exception. Here I'm trying to put, I've got 2 slots and I didn't provide enough data. All right, if I provide enough data, then I will have a program that compiles and runs. Always be sure you have the right types and you have the right number of parameters. If the only thing you can get away with is providing too many parameters. That will still run, but I still probably have a bug, right? I intended to output this 10 somehow, and I haven't actually put in a 3rd slot. So I probably intended something like that. That won't cause a runtime exception. That's just probably a bug in my program. All right, so final thing to test your knowledge of whether you've learned anything about the printf. I suggest you pause the video and see if you can match. So there are 2 matching here, the red matching and the blue matching. They're separate. Try and match the code with what it's going to output. So match the code with the letter and then match these code segments with the numbers. So what is the first one? Well, that's a %f. So it's a floating point value. All right, and I haven't specified the number of decimals I want to output, so at least my version of Java, I don't know if this is actually part of the Java spec, or it could be, it may vary on different computers, I'm not sure. But it's going to do something like produce 4242 with 6 decimals. %d, and I've got 4242, well, I've not specified anything fancy. There's no problem. I've got an integer. I can put it into a %d slot, and I'm going to get output A. 0.2f, the 0.2 specifies 2 decimals of output, and even though this 4242 only has 1 decimal, it's going to format it like there are 2 decimals. All right, and I'm going to get output B. I've got 4242. I've cast it to a double, which was important because this is %e, and recall %e is that scientific notation. And so I'm going to get format here with 3 decimals after the 3 decimals in the first part of the scientific notation, and I'm going to get output C. And that leaves us with D. The comma specifies put commas between groups of 3 digits. The blue section, all right, this one's got a little more tricky. %d, 42, and 42. All right, which one's that going to produce? Well, that is just going to produce 2. All right, it's just going to put the 42 in the first slot and the 42 after the second slot. I didn't put a space between this and my format specifier, and so Java is not going to put a space in it either when it outputs it. Is this going to add these 2 numbers? No, it's not going to add them because this is just the format specifier. So %d is going to get replaced with 42. The plus is between the double quotes, and so it's literally just a plus character, and you're just going to get the plus output. So you're going to get output 1. What are you going to get in this one? Well, recall you have to have the right number of parameters after to fill into each slot. I've got %d and %d, and I've only specified a single slot. And that's a runtime error. That's going to crash. %8d, 8 is specifying, because there's no dot in front of it, I know it's actually specifying the minimum number of characters. So whenever this 42 is output, it's always going to be right justified with 8 characters of 8 characters of space, and that's going to produce output 3. If I put a minus before that, it's going to left justify it, and so it's going to do 42, and you can't really see, but there's 6 extra spaces or something in here. Finally, the last one, that's also a runtime error. So recall, you can't put the wrong type into the slot. Alright, so to summarize what we talked about today, we looked at libraries. So libraries are just a collection of methods that are helpful for people trying to build a certain kind of program, and you've already used libraries loads, things like standard draw and standard in. Wherever possible, you should make use of existing libraries, or if you can split out common functionality between your programs into a library, that's a good thing to do. It's easier to understand your code, it's easier to debug each of the libraries, and maintain and improve the libraries and reuse them. And then finally, we looked at a common way of handling output in Java and in other programming languages, which is this printf. And printf takes percent codes. You make a format specifier inside of a string with little secret percent codes, and then provide a comma delimited list of the variables to fill into those slots.